solid and liquid. So from this table, we can see that most of the K or most of the segregation coefficients, its value are less than 1. So which means that the concentration in your liquid will be larger than the concentration in your solid. Okay, so this concentration is defined as your number per like centimeter cube, yeah, something like that. Okay, and and last time we say that we choose boron as the preferred dopant because the coefficient is close to 1. Since the impurity, they tend to stay in the liquid. So when you pull the crystal, okay, you can imagine that the impurity concentration of the liquid will continue to increase as you pull the crystal out of your liquid. So once the liquid they turn back to solid, then those impurity concentration in your solid will also increase. Right, so you can imagine that the ingot from the beginning to the end of the pulling time, the concentration will keep increasing. And so we can use a simple physical model to describe this kind of phenomenon. Okay, so here we define this. Supposedly in the beginning we have like V0 or VO. This is the initial volume, and we have the initial number of impurities, is I0, and so the C0, the initial concentration, which is defined as your I divided by your V, right? Okay, and this IL and CL or BS, CS, they are defined as the impurity or concentration in your liquid and in the solid at a certain time, right? So during the growth, we can we see that there's as time goes by, some volume will become to freeze, right? So we will have dVs, which means the volume that increased at a certain amount of time will be the volume that decreased in the liquid, and we can define that as the dV. Okay, that's the additional volume per time, right? We have this volume to freeze and turn to the solid state. So during this starification time, and the impurity incorporated into this volume can be defined as like this, right? And this K times C will be the total concentration in the solid, right? As we check this equation again, the CS divided by CL. So your K times CL will be your CS. Right? That's the concentration in the solid. And you times the volume, and you will get a number of impurities. So that's called DI. Okay? And then we can write CL as the total impurity number IL divided by V0 minus Vs, which is the original initial volume minus your solid. Okay, and then we can do that very simple arrangement. So it becomes like equation 13, and we do the integration, and we find out that our I and the impurity has a relationship with your volume and with the segregation coefficient. And from this equation, we can see that this Vs is the volume that turn into solid. So in the beginning, Vs is equals to 0, right? So your IL will be equal to your I0. I think this one is 0, right? So no matter what's number of your K0, then I is equal to I0. But once you have after you finish all the crystal growth, your Vs will equals to your V0. Then this term will turn to 1. So 1 minus 1 is 1 be 0. So at that point, your IL is 0, which means that all the impurities are now in the solid now. So we can draw. Actually, we can divide it. We can derive this the number of impurity, and you can turn it to the number of concentration. Right. So in here we can define this Vs. Okay, we can define this this Vs and the ratio between Vs and V0. We can define the number of this fraction of melt frozen as F. Okay, so that equation we can write in this form. And now, since we know that your impurity or concentration can be, you can use this equation to calculate the concentration. Right? So it's proportional to your I dI over dV. So we can plug this one, and from this equation plus this one, we can get this equation 16. Okay, so it describes the impurity concentration in the resulting wafers based on their location in the crystal. Their location means when you increase the time of your growth, then this number will continue to change, right? So that will correspond to the certain location in your ingot. Okay. So we can plot this equation 16 into these figures. Right, as we can plug in different segregation coefficient here, and this is the in the x-axis is the fraction of melt that solidify, which means this is F. So here F equals 0, that means that's the beginning, right? And F equals 1 means all the liquid now they all turn into solid. So in the y-axis, the ratio CS over C0, which means we try to define the concentration, impurity concentration in your solid, and compare it to the initial impurity concentration. So since this boron K is equals to 0.8. So you can see that during the growth, the whole process, you can see the boron will give you a more uniform impurity distribution among your ingot. And if you have this segregation coefficient less than 1, then you can see from the beginning to the end, the impurity concentration in your ingot that will vary a lot. Right? For example, this antimony. Antimony here, if you compare in the beginning the material, the concentration looks like this, but in the end of your growth process, you can see your impurity concentration increases a lot. And if you compare this to this, and this, you get a 1 order of magnitude difference. So, and that's why last week we said if you want to choose the dopant in your silicon during your crystal growth, we'll find one that the segregation coefficient is more close to 1. That will give you more uniform distribution of your impurities in your ingot. So once you cut into different wafers, you don't have, I think the impurity among wafers will be more uniform. Okay, so here is another figures that we can plot all the segregation coefficient into that equation and plot these figures. And again, you can see this is the segregation coefficient less than 1, and here are the case for the number larger than 1. And again, if the number is deviate from 1, then you can see in the beginning and the end, the impurity concentration will vary with your position a lot. Okay, and here is a more realistic model which describes the concentration as an interface between your solid and liquid. There may exist concentration that is a function of your position. Right? So if you consider that change in your during your calculation, then we can try to modify our segregation coefficients, and it will turn into like this. And here is another more realistic numbers, and of course it's more complicated. So but we won't spend too much time on this. It's just for your reference. So if you want to model the like concentration in your ingot during your FZ process, no, the CZ crystal growth process, then you have to consider that this kind of more realistic model. Okay, so now we get into the FZ growth, and this method can also be used to refine your crystal, which means to purify your crystal. So let's consider we have a material already is here, and we can move this coil, and we can move in these directions. So this is the original concentration in this ingot or in this rod, and this is the concentration in your solid, which is refined or purified after you moving your coil from in positive X directions. So that because of the effect of segregation coefficient, then you can imagine this CS will be also a function of your position. Okay. Okay. So now we have this DI number. Okay, which equals to the C0 minus K times CL. Okay, so those impurity that originally exist in here, and then once you melt it, and they will tend to stay in your liquid. So when it turns into solid, then some of them will be stay in the solid. So that causes the reduction of the impurity in your liquid. So it's very easy for us to write this equation. And of course, there are more derivation in the textbook, so I don't put all the equation in here. But in the end, okay, we can do some rearrangement, and we can plot like these parameters in your equations. And also similarly, you can do the integrals, and this will be the final result of this concentration is function of your position. Okay, so here we have an exponential term, we have segregation coefficient here. Okay, so we can plot the figures, and there are two figures we showed here. On the left hand side, you can see the effect of your segregation coefficient. If you have this number like less than 1, okay, very similar to the figures in the CZ model that we just introduced. You can see we change, if we check the concentration as a function of your position. That's the beginning, and here is the end. If your K is close to 1, then K is more uniform. But if your K is larger than 1, which means the concentration in your liquid and your solid, the ratio is very, very large, right? So you can, if you do the purification in this process, then in the beginning, then you will get a very pure material in the beginning, right? But in the end, the difference between these two will be larger compared with the number with coefficient close to 1. But if you choose the dopant coefficient close to 1, in that case, when you do this purification process, the effect is not that you can see it's not very effective, right? So once you do this one time, then you didn't reduce the impurity in your solid a lot. Right? You see this difference? You understand that? Okay. 就是如果你这个是接近1的话它前后虽然看起来是 uniform， 可是它的效果就没有这么好。因为它那个差距越大的话 if the number of this segregation coefficient, if it's larger, which means that the impurity concentration, the ratio is larger. So if we want to do, if you want to purify this material, then it's more effective to choose the dopant, the coefficient way less than 1. Okay, 就是它的那个效果会比较好。But you can also do this like several times. So, for example, on the right-hand side, you do this 1 time and do this 5 times. Okay, so in the beginning, you can see you can drop the impurity coefficient a lot. And here, also, you can find out you can decrease the impurities. Right. Okay. And now we will get into the modeling of point defects. And this part is quite tricky because it's always like a lot of difficulties modeling the defects. Okay, and the equation we introduce you here will come from a different, either from some simulation papers or because it's very difficult to use experiment to verify this. So you just give you a sense of the way that how can we model this point defect. Okay, the point defect in the last lectures we talked about we have V and I, which means your vacancy and interstitials. Okay. And because you have those defects that will help you to reduce the total energy, this free energy of the crystal, which means you give you a more stable crystal. So that will justify their existence in lower temperatures, right? As long as it's not equals to absolute 0. So this concentration can be written in this form, which is related to your like entropy or enthalpy, and like your lattice size of your density of your number of density of your lattice size. Okay, so it has like this kind of parameters, and of course is a temperature dependent number here. Okay. And here we just try to recap what kind of defect we have in the last lecture. The first one is a Frankel pair. It's by moving one second atom off from a lattice side inside a crystal, and it creates equal number of V and I. Okay, and so I is created if this second atom move away from from the surface into its bulk. And V and I can be recombined, and removing one of each. Okay, so you can generate a V and I at the same time, and also if they recombine, you can they will disappear at the same time. Okay. And also we have staking form can create capture either V and I by growing or shrinking but one lattice size, which means this V and I they will segregate to like certain point, especially you have staking fault. And in general, is related to this kinematics, and is assume that those process will change immediately with respect to temperatures. Okay, so that's those general information that we have to keep in mind regarding this defect, their characteristics. Okay, and here you can just directly get these numbers. Like we plug in all the parameters here, and we can write this estimation equations for our I and V concentration in your crystal. Okay, so these numbers, well, they some empirical number we can use. And again, and for example, if we describe that during the CC growth process in very high temperatures, or during some annealing process at very high temperatures, we can give you this point defect numbers. And from this defect number, you can see that it's very small compared to either your dopant concentration, donor or receptors. Right, this is like 10 to the 12. 10 to 12 is like, at this you have 15 to 20. So, okay, so to be honest, it's very difficult to use some experimental measurement to measure the concentration of the defects. But they are present because when you do some experiment, you will observe some phenomena that can only be explained by introducing some defects in your model. Right. And okay, in this defect they are mobile, which means they will move around in your crystals, and it's not very easy to directly measure it. But we can infer from, for example, this dopant diffusivity. Right? That's the experiment that I just mentioned. That if you don't have defect, it's easy to you can see the dopant profile after they diffuse in your material. But once you have like very bad with many defects, most in these crystals, and we measure the dopant profile again, you'll find out that your dopant will move faster more purified material. So people begin to think that, okay, so what caused this diffusivity to change a lot? And so this, they come out with this defect existing model. So that's the diffusivity of your I and V in your material. Okay. I think in the last lecture we introduced these figures here, and here, okay, I believe I already talked about this, and also, right, in general, your I and V, they can be different, okay, and they are functional temperatures. Okay, and here is the model that proposed by Shockley and Last in 1957. Okay, they describe this charge defect concentration because you have defects, and that will create additional space in your material between your conduction band and valence band. Right? Originally, there we call it this forbidden region, forbidden gap, that you don't find any space in between this band gap. But you have defect that will create this kind of state. And once you have electron hole populate this state, then you will change your defect. The charge neutrality will be changed. Okay, so here we have like V plus or V plus plus or V minus or V minus minus states that and this dashed line here, this is EI, which means is in the middle gap between your band gap, and this is EF, is your Fermi level, and this illustration, you can see the EF is more close to your conduction band, which means it's N-type materials. And the state below your Fermi level, that means your this high probability that you can find your electron populate in these states. Okay, so you can imagine that during these states you can find the electron more easily, right, in these states. And the state, the energy difference or the energy levels between these states, some people use some calculation can give you this number. For example, this is the V state, okay, and between your EC and EV minus. Okay, so here are just some numbers that for you, and you can refer to this number when you do these calculations, and some value that are unknown or uncertain. But this number is from this from the papers, but you can check if there is more updated papers that describe this. Okay. So we try to calculate these numbers, all right? These defect numbers. So we need to find out like what's the probability that you can find electron in these states. Okay. Firstly, for intrinsic silicon, no change in charge occupation, and for extrinsic like N-type silicons, your V, these two states will dominate because your Fermi level will be changed among this region. So depends on your dopant concentration, right? So which means that your V minus and V minus minus, these two states will dominate when you do the calculations. And this dominant vacancy charge state becomes like acting like a receptors, right? Because they will accept your electrons. And for the P type, now this P plus, or V plus and V plus plus states will dominate, right? When you energy label change this region. And this region will become like a donor. Okay. And Shockley can describe this equation here. And these defect states, these defect concentrations are always less than your intrinsic concentration. Of course, it's compared to your dopant or your intrinsic concentration. This level is like 10 to the 10 or 12. Okay, still less than your intrinsic concentration, which is like also like 10, 12. Okay, and okay, so this point defect concentration will change with your dopant, right? Because your dopant will affect your Fermi level, which will affect your point defect concentration. Okay, and here just give you an example. When we do the diffusion or implantation and create this PN junction profile like this, and we can quickly calculate these numbers. And this is the band gap, and we plot all these parameters, these numbers, and we can draw this band diagram. It's 0.11, 0.57. So okay, so once we have this band gap plotted here, and then we can. This is for these P regions. Yeah, but in the N region, you can see your Fermi level now is more close to your conduction band. Right? This is the intrinsic Fermi level. It's roughly in the middle of your gate. Okay. So once you move this Fermi level to this this region, then you can get you can plug into these equations, and would you give you numbers showing this table? Okay. This is the dopant concentration 1 times 10 to 15, and it's 590. And here is the intrinsic concentration, around like 18 in this 1000 degrees Celsius, which is quite high. And then we can calculate this this neutrality charge and also the negative charge or positive charge in this vacancy state. And here is the interstitial states. And we can get this number that's like 10 to the 14 or 13, and it's also like 10 to the 14 to 15. Okay, so from this number we can observe that your intrinsic concentration, because of this process temperature now is at 1000 degrees C. Your Ni is actually related to your dopant, right? That's comparable to your dopant concentration now. Like for example, this one is even larger than your intrinsic concentration, 15. And this one is comparable to your 10 to the 19 dopant concentration. concentration here. And like for this V0 charge, its concentration is the same in these two regions. And you can see that different charge states will dominate in different regions. Like these two and like this one will be dominating this P region or N region. Okay. So I think if you are really interested in this defense physics, you have to check with some solid state textbook. Right. Okay. Now, during the CZ growth, we will introduce oxygen and carbon because of your environment, because of your crucible. So we will have to incorporate this oxygen and carbon in your material. And typically, this oxygen and carbon concentration that 10 to 18 and 10 to 16. Okay. So this one, 10 to 18, is quite significant already. So so it often will precipitate to form like small silicon dioxide in your crystal. Like for example, here we have this oxygen, which is the interstitial state oxygen, will to precipitate. This SiO2 will begin to grow larger and larger. And once they begin to grow, they will need this V to be participated in this process, because you need space. So you need V defects to get into this process. And in the meanwhile, you try to kick out some interstitials during this process because you just need space, right? So this equation will describe it, what I just said here. During this from oxidation process, you change from silicon to silicon dioxide. Then you have to incorporate this V. So if you have more V, then you will change the process to the right-hand side. But or you have to either you increase V or reduce I. Okay, so that will enhance your oxidation process. And also during this process, you will of course introduce some stresses on your materials. And this formation of SiO2 will help us to do the gathering process, as we are going to talk about this in chapter 4, the next chapter. Okay, and here are some key ideas that I'm trying to summarize in these chapters. And the first one is this SiO2, this raw material. We use SiO2 to refine it and produce some electronic grade silicon that can be used for our IC process. And we introduced the CZ crystal growth, and that will give you a single crystal silicon. Okay, but in this process, you have oxygen and carbon, and these numbers are in measurable quantities. And the dopant incorporation during this crystal growth is very straightforward. We can add some dopant in, but we have to be careful with our segregation coefficients, because that will create these spatial variations. Okay, that's the uniformity between your wafers. And we also introduced this point line and volume defects the crystals, and especially you can after some high temperature process, you can incorporate this defects. Okay, and these defects are fundamental, right? Which means they will exist in your crystals, and those concentrations are the function of temperatures. Right? And during the fabrication process, like I implant here, that will create this non-equilibrium transient concentration of this defect, and that will change like your dopant diffusion constant. So that we call it the transient enhanced diffusion. So you will have larger diffusivities in your materials because of these defects. Okay. Now we can just move into this chapter 4. Okay. Okay. So we before we get into each step of the fabrication process,